Yes, any questions? You see, this strategy in this, in obtaining the potential when there's a dielectric is basically the same as what we had done before. You just divide your space into regions in which your potential satisfies the Laplace's equation. So find the general solution of the Laplace's equation in whichever coordinate system you use. And then the potential should be continuous across the boundary, and the perpendicular component of not the electric field this time, but the displacement field. Well, if there are no free charges, the perpendicular component of the displacement field should also be continuous across the boundary. And that allows us to determine all the unknowns in your general solution. Any questions? No. I don't think I will start the magnetism chapter today. So let's do another example with dielectrics. This will be another one of the examples that we have studied with conductors, but instead of a conductor, I will just assume that we put a dielectric. So we have this our space. Our space is divided into two. Half of our space, there will be a dielectric, let's say dielectric constant epsilon 1, the permittivity epsilon 1, and the other space is, we have permittivity epsilon 2. Or let's take it back for simplicity. The idea will be the same. We have half of our space is filled with a dielectric, and we put some charge in front of this dielectric cube. So what is the electric field everywhere, potential everywhere, what are the bound charges, etc. Now, we will be solving this problem in various different ways. So let's start with method 1. This is the method in your book. Well, there will be some bound charge over here. And we know that the bound charge, let's take this as our z-axis. Bound charge will be nothing but p at the normal direction, pointing from the dielectric to the outside. But this is nothing but the z-axis, so this is pz. This is the bound charge. Well, we don't know what the polarization is, so this doesn't really help that much. But let's say pz, we know that this is a linear dielectric, so the polarization in the z direction will be proportional to the electric field in the z direction, with the proportionality constant epsilon 0 times chi e. Chi being the electrical susceptibility. So if we knew what Ez was, just inside our boundary, inside our dielectric on the surface, then we could determine the bound charge. Well, Ez will basically receive two contributions. One from the charge Q, there's the Z component. Let me write it in this form, EQZ. This is the electric field due to the point charge. Plus, there will be another component of Ez which will be created by the surface charges. But this electric field created by the surface charges, I mean, if you are right very close to the surface, the electric field is given only by the surface charge density, and the electric field is nothing but sigma over 2 epsilon 0. So see, the bound charge density is nothing but epsilon 0 chi e Ez due to the point charge Q plus sigma b over 2 epsilon 0. But this equation is kind of trivial to solve for sigma b. Sigma b is equal to chi e over 2 sigma b plus epsilon 0 chi e Ez. Or sigma b is nothing but epsilon 0 chi e twice epsilon 0 chi e divided by 2 plus chi e times Ez cube. What is Ez cube? Well, at this point, this charge, let's say this is distance d, this distance, let's call it r. The electric field will be in this direction. Let's say this angle is theta, this is EQ. EZQ will be nothing but 1 over 4 pi epsilon 0 Q over the distance squared is r squared plus d squared times cosine of theta. It's in the minus direction. Well, cosine of theta is nothing but d over r squared plus d squared square root. This is equal to minus 1 over 4 pi epsilon 0 qd over r squared plus d squared to the power 3/2. So let's do some simplification. This epsilon zeros, let's just cancel epsilon zeros only. So this will be equal to minus twice chi e over 2 plus chi e 1 over 4 pi q d over r squared plus d squared. This is the bound charges. So we know the bound charges, we know the free charge, we basically know all the charge distribution everywhere. And since we know the charge distribution, from this charge distribution we can calculate the electric field, the potential, etc. But let me remind you another problem that we had solved. If you remember, we also solved this problem of a point charge in front of a conducting plane. So we had this conducting plane, grounded conducting plane. We had put some point charge over here. So basically there was this image charge on the other side, exactly at the same distance, with exactly the same magnitude. And so the electric field lines looked like this. And in this problem, we also calculated the induced charges. On the plane. This was, let me just say, proportional to 1 over r squared plus d squared to the power 3/2. So the dependence of the charge density in this problem on the position is exactly the same, which kind of indicates that we can also use the method of images in this problem. So that is our method to using the method of images. We can determine the electric field and the potential and also the surface charge density, the bound surface charge density if we want. Method of images. Now, of course, in the case of the conductor, we already know that in this region the electric field was 0. But in this case, it will not be 0. So this is epsilon. Let us say epsilon 1 and epsilon 2. And we can have two different dielectrics. In between, there is an interface. And let's say this is region 1. This is region 2. So we need to find two different potentials. one in region 1, one in region 2. And we will do it by using the method of images. So the image of this charge will be here. We don't know what the magnitude will be. At least if epsilon 1 is equal to epsilon 2, the magnitude should be 0. That is one limit we know. So V2, the potential in region 2, is, well, 1 due to this plus Q charge, 1 over 4 pi epsilon 2 Q over R minus, let's say, R1. This is at position R1. This is at position R2. Plus 1 over 4 pi epsilon 2 Q prime over R minus R2. So it's just, the method of images tells me that if we are in this region, I already see this plus Q charge, but all the other the effect of all the other dielectric, I can just model it as if I have a single dielectric, not I'm using the same dielectric constant, same permittivity in both of these terms. Everything is uniform, but the effect of the other dielectric is just to create that image charge. So I have two charges, one at R1, the other one at R2. I have a uniform medium. Everywhere has this dielectric constant epsilon 2, so this will be my potential. Well, this is my ansatz, let's say. Of course, now we will be using the uniqueness. I mean, just imagine looking at a mirror. Let's say we have a mirror. What we see in the mirror is our side. So it is as if the other side of the mirror is just like our side. This is exactly the same idea. So we have this mirror over here. The observer looks from here, so it sees only its own side. Everything is homogeneous. Now, this is not really an assumption. At the end, it might turn out that, for example, Q prime is epsilon 2 over epsilon 1. Then epsilon 2s will cancel, and I will have epsilon 1 over here. It's not really a big assumption. It's not even an assumption. Or you can also look at it the other way, in this way. These images are basically the charges in this region, at this surface. So their electric field is always in epsilon 2. Their electric field never goes in region 1. It's just, it looks as if it is coming from this point. Now let's look at V1. Well, you are an observer. On the left-hand side, what you will see is these surface charges over here, which will behave as if there is a point Q prime charge on the other side at the distance d. So this Q prime will be overlapping with that plus Q. So for an observer on this side, it will only see a single point charge at the position of my original charge. Let me just call that Q double prime. My intuition tells me that this Q double prime should be equal to Q plus Q prime. Let us check. Now this intuition, let's say, is based on the fact that these image charges are nothing but the bound charges on this plane. And these bound charges on the plane, they just behave like a point charge on the other side at a distance d. So these bound charges, if you look at it from this side, those bound charges will look like they are coming from a charge Q prime on this side. If you look at it from this region, those bound charges will look like they are coming from a charge Q prime on this side, which overlaps with our original charge. So at the position of my original charge, I will just see Q plus Q prime. Q because it's already there, plus Q prime because of these bound charges. So this is 1 over 4 pi epsilon 1 Q double prime over R minus R2. R1, sorry, this is R1. R1 is the position of this charge over here. R2 is the position of the charge over here. Well, you can also say, keep it this way. This is my ansatz. Does it work? Let's check if this works. I'm just claiming that, or postulating that, the observer over here sees a single charge Q double prime at that point. The observer here sees the charge Q prime and also this Q. So let's determine what this Q double prime and Q prime are. Those are the things that we will need to determine. Yes? You see, this V1 is the potential over here. I'm in the region with dielectric constant epsilon 1. Of course, as I said before, it might turn out that Q double prime is epsilon 1 over epsilon 2 times some other number. Then here, epsilon 1s will cancel. I will end up having epsilon 2. It doesn't really matter. You see, Q prime is not the real charge. There's no such charge, but there are charges on the boundary, on this plane, which behave as if there is a charge on the other side. So it's just like, you have probably looked at a hologram. When you look at a hologram, you see as if there is a face on the other side, for example. If you look at the other side of the hologram, you don't see the face.
Hocam şimdi bu V1 ve V2 şey mi yazıyor? Yani V2 bu region 2'deki observer, V1'de oradaki.
Yes.
Peki region 1'deki observer, region 2'deki potansiyeli yazar mı?
You see, these are the, forget about the observers if you don't like the term. It's not really the observer. We are writing down the potential at the point R. Is this point R in region 1 or in region 2? And we are neither in region 1 nor in region 2. We are writing the potentials. So of course the observers can write it down, but the problem is what is the potential in region 1, what is the potential in region 2? If you want to measure them, you have to go there. And when you go there, you will just see a charge on the other side. Yes?
Q double prime, the image of Q prime?
No?
Yani hocam Q double prime'in içinde hem indüsteden hem de kendi yükümüz mü?
Yes. You see, the idea here is image charges do not exist. The only thing that exists are the bound charges at the interface. And the claim is that the bound charges on the interface are such that they behave as if there is a point charge on the other side at a distance t.
Yani hem indüstriyel hem de diğer nasıl o zaman aynı şeyde pozisyonda olabiliyoruz? Yani sonuçta ikisinin arasında D kadar bir mesafe var.
Sure, but you see, the image charge, the bound charges over here, they behave as if there is a charge on the other side at a distance t. So if you are an observer over here, you will see these bound charges. which behave as a point charge at a distance d on the other side. If you are over here, you will see these bound charges, and also this one, which will, the bound charges here though, will behave as there is a point charge on the other side at a distance d.
O zaman şu Reci 1'deki observer sadece bound charge'ı görüyor aslında.
Not really. I mean, you see, my claim is this one. The bound charges create the charge q prime. The q is the charge that we had put there. So if you are over here, you will see the bound charge plus the q, if that claim is correct. But the bound charges also behave as if they are exact overlapping with the charge q. So essentially the total charge that, if you are over here, the total charge that you will measure will be the sum of the charges due to this bound charge and also the q.
O zaman şu V1'e neden artı Q prime eklemedik?
Well, let's q prime. I mean, if my intuition is correct, well, those terms are the same, so I can just combine them. So 1 over 4 pi epsilon 1 r minus r1 times q, 1 over 4 pi epsilon 1 r minus r1 and q prime. If I combine them, I will get q plus q prime, which I call q double prime. So q double prime is basically the effect of the image plus the original charge. Well, that was kind of my intuition, so I rather not put it yet. Eventually, if that comes out to be correct, then everything fits. If that turns out not to be correct, then we have to think something else.
Yani hocam ben aynanın bu taraf, aynanın içine girdiğimde görüntü dışarıya mı katlanıyor?
You are not going inside the mirror. This is a double-sided mirror. Double-sided in the sense that both sides are mirrors. Let's solve this potential first, and then we can continue. Maybe some of your questions will be answered on the way. Well, what do I know about the potentials? First of all, they have to be continuous. Well, on the interface, r minus r1 is equal to r minus r2. This is what we have on the interface. So if you take any point over here, this distance is equal to this distance. So just omitting common factors, both the potentials have this 1 over 4 pi times the distance factor. What we end up having is q plus q prime over epsilon 2 should be equal to q double prime over epsilon 1. Okay, my intuition was kind of wrong. Q plus q prime is not equal to q double prime. Then next thing, there are no free charges. So D has to be the displacement field, the perpendicular component has to be continuous. So that tells me that epsilon 1 del V1 by del Z should be equal to epsilon 2 del V2 by del Z on the boundary. Yes. So I have two unknowns. I don't know Q prime and I don't know Q double prime. I need to determine two unknowns, so I need two equations. This is my second equation. So let's see. I have this 1 over R minus R1. I need to take the derivative of this thing with respect to Z. And then set Z is equal to 0 for my boundary. This is equal to 1 over del Z. X, well, let me also choose some directions. This is my Z axis. X in the X hat plus Y in the Y hat plus Z in the Z hat. This is my R. Minus R1 is just D in the Z hat. Sorry, that's the Z derivative, not X. I'm just taking some arbitrary point. I'm right. I will be evaluating the potential at an arbitrary point. I need to know the 1 over the distance of that point from the Z hat, which is my R1. This is equal to derivative with respect to Z of 1 over X squared plus Y squared plus Z minus D squared to the power 1/2. Of course, evaluate that Z is equal to 0, which is equal to minus Z minus D divided by X squared plus Y squared plus Z minus D squared to the power 3/2. Evaluate that Z is equal to 0. I just took the derivative. Now when I set Z is equal to 0, this is just D over X squared plus Y squared plus D squared to the power 3/2. Which is equal to D over R minus R1 cubed on the boundary. Now I can do the same thing, 1 over R minus R2, but you see R2 is basically the same thing as R1, with the only change that instead of D, I have to put minus D everywhere. The derivation will be identical, so it will be minus D over R minus R2 cubed on the boundary. So these are my potentials. I need to take their Z derivatives on the boundary and equate the two. So epsilon 1 times 1 over 4 pi epsilon 1 Q double prime over R minus R1 cubed times D. This is the derivative of V1 on the boundary with respect to Z. This is equal to epsilon 2 times 1 over 4 pi epsilon 2 times Q D over R minus R1 cube minus plus Q prime times minus D over R minus R1 R2 cubed. everything is on the boundary. Now let's do the cancellations. Epsilon 1's cancel, epsilon 2's cancel. 4 pi is cancelled. On the boundary, r minus r1 is equal to r minus r2. This cancels, this cancels, this cancels. So what is left is q double prime d is equal to q times d minus q prime times d. Or q double prime is equal to q minus q prime.
Peki şu önceden bulduğumuz şey ne olacak? Hani Q nasıl Q prime oluyor?
And that is our other equation.
Başta yaptığımız hesap şimdi hiç hoşumuza gitmemişti ama çok güzel yapılacak.
Really? So let's see, let's continue. Q double prime is Q minus Q prime over epsilon 1. Now we have to solve this equation for Q prime. So Q times 1 over epsilon 2 minus 1 over epsilon 1. This is equal to minus Q prime times 1 over epsilon 1 plus 1 over epsilon 2. So this is equal to epsilon 1 minus epsilon 2 divided by Q, divided by epsilon 1 times epsilon 2 multiplied by Q. This is epsilon 1 plus epsilon 2 divided by epsilon 1 times epsilon 2 times minus Q prime. So Q prime is just epsilon 2 minus epsilon 1 divided by epsilon 2 plus epsilon 1 times Q. Q double prime is equal to Q minus Q prime, Q 1 minus epsilon 2 minus epsilon 1 divided by epsilon 2 plus epsilon 1, which is twice epsilon 1 divided by epsilon 1 plus epsilon 2 times Q. Now let us plot the electric field lines. Well, you see, the potentials obtained by these image charges satisfies our boundary conditions, our equations, and hence the uniqueness tells me that this is the only solution. So if we would just go back to method 1, pick up that bound charge and integrate put it in the expression of the potential and integrate it, we should obtain exactly the same potential. Now let's see. This is our Q. Here we have Q prime. This is epsilon 1, this is epsilon 2. Now first let's look at the case, what happens if epsilon 1 is larger than epsilon 2? We have these two dielectric mediums. So it might happen that here this is vacuum, so epsilon 2 is 1. So epsilon 1 will be larger than 1. So what will happen if epsilon 1 is larger than epsilon 2? So the Q prime will be negative. Q prime is epsilon 2 minus epsilon 1. If epsilon 1 is larger, Q prime will be negative. Well, if Q prime is negative, so we have a negative charge, we have a positive charge. If you would draw the electric field lines will start from the positive charge and they will bend towards the negative charge. So the electric field lines, well, let me just draw them closer. So the electric field lines will start from the positive charge. They will bend toward the negative charge. But then the potential on this side is the potential of a single point charge, not two charges. But the potential of a single charge is just, electric field lines are just radially out. So the electric field lines on this side will be just radially outward lines from that charge. So these are how the electric field lines will look like. They are not continuous. There are corners or kinks at the interface.
John, why will they continue reading? Why will they continue?
Well, let's look at the potential in region 1. You see, this is our potential in region 1. The electric field in region 1 will be just the electric field created by a single point charge located at R1. And the electric field line of a point charge, they are just radially outward lines. So in region 1, the electric field lines are just radially outward lines, and they, if you would extend them, they would just converge at the point R1. These are just the electric field lines corresponding to this potential. We are not looking at a conductor. This is not a conductor.
Q'da bir prime olması, yani burada ikinci bir image olduğunu gösteriyor bize. Yani şimdi endüstriyel bir de image mi oluşturuyor? Hani niye iki tane image'imiz var?
Well, the image doesn't exist. So there's no image. But what happens is some charge distributions behave as if there is a point charge on the other side, which doesn't exist. In some systems. Planar systems are such systems. So if you have a planar charge, whether one side is a conductor or a dielectric, it doesn't really matter. If you have this planar system and if you put a point charge, which will create some surface charges here, which behaves as if there is a point charge on the other side. So that is the whole idea of the method of images.
Ama o zaman bir tane, hani çünkü o sanki orada hani bir yük, yani image biliminde o yük varmış gibi biliniyor ama hani niye o zaman burada bu prime'ımız var?
Well, okay, so first let's finish this one. Okay, then we will go back to the first method. Continue with the first method. Now let me look at the other limit. So any questions on this one? In this case, epsilon 2 is less than epsilon 1. Since epsilon 2 is smaller than epsilon 1, Q prime is negative. Now, if epsilon 2 is larger than epsilon 1, you see Q prime is positive in this case. So we have Q, we have plus Q, we have Q prime, which is larger than 0. Now this time we have two positive charges. That is, in this region, the potential behaves as if there are two positive charges, one here, one on the other side. So the electric field lines will start from this positive charge, and they will bend away from that other positive charge. And again, once they arrive at the boundary, on this side of the boundary, there is still a single charge on that side. So the electric field lines are still radially outward from that point charge. So this is how they will bend. Now, also, if you just look at the dipoles at the interface, you see, due to this positive charge, you will be creating dipoles at the interface also. If epsilon 1 is larger, well, you see, this is the positive and this is the negative, this is the positive, this is the negative. Well, if epsilon 1 is larger, it just means the dipoles created in epsilon 1 will be larger, bigger. That is, the negative end of this dipole will be more negative than the positive end of the other dipole on the other region. So in total, at this interface, we have this plus this, but this minus is larger than this plus in magnitude, so the sum will be negative. So here we have a negative surface charge. So that is why we have a positive charge on the surface, we have negative bound charges, so the electric field line just bend towards this interface. Whereas on the other case, if epsilon 2 is larger than epsilon 1, again, just consider the dipoles, minus plus at the interface, plus minus. If epsilon 2 is larger, then the positive in magnitude is bigger than the negative over here. So when you sum the charges of these dipoles at the interface, the net effect will be it will create a positive charge on the interface. So this surface will be positively charged, and hence the electric field lines coming from a positive charge will bend away from this surface.
Why is the positive charge stronger than the negative charge in magnitude?
You see, it is determined by the dielectric constant, by the permittivities. So you see, the larger permittivity just means it's easier to create a dipole. So it's easier to separate charges. Either you can say that you separate the charges by equal amounts, but a larger charge separates. So more positive charges, less negative charges. If epsilon 2 is bigger than epsilon 1, this will be more positive than this is negative. So the sum is positive. Now let's go back to method 1 and try to combine it with this one.
Hocam bir şey soracağım. Method 1'da biz separation of variables.
No. You see, what we did in method 1 was kind of a clever trick. That, well, the bound charges we could write in terms of the electric field, which we could write in terms of the free charge and the bound charges. That gave us an equation for the bound surface charge density. And by solving that equation, we could determine the bound surface charge density. Once we know that bound surface charge density, well, we can just write down the potential and the electric field. The total electric field is just the bound charge at the point r prime times ds. ds times the bound charge density just gives me the charge, 1 over 4 pi epsilon 0. This is the electric field at the point r. R minus r prime divided by r minus r prime cube plus 1 over 4 pi epsilon 0 q r minus r1 divided by r minus r1 cubed. Now that is what I'm thinking. Should it be epsilon 1 or epsilon 2 or epsilon 0? I'm sure that that is epsilon 0. Of that one, I'm not so sure. I will be sure if you let me just write q double prime over there.
Q yazdıysak epsilon 0. Q yazdıysak epsilon 0.
Epsilon 1 or epsilon 2.
Epsilon 2.
You see why? What we had done, if you just, what is this bound charge, surface bound charge, etc. So we have this dielectric, and if we could know all the position of all the charges everywhere, including free and the bound charges, then we have 1 over 4 pi epsilon 0, ds times sigma, and these are all epsilon zeros, if we would know all the charges, etc. But we don't, because there are these bound charges which we are not really controlling. But it turns out if you just create some electric field by, let's say, putting some charges in our dielectric, or you can apply an external electric field, etc., you create bound charge distributions, either on the surface or on the boundary. And the effects of these polarization and the bound charges, we can take into account by using epsilon in terms of epsilon 0. So this replacing epsilon 0 by epsilon already takes into account the bound charges. You see what we have. If you have a single charge on a dielectric, we know that the divergence of the displacement field, which is the divergence of minus the divergence of epsilon times the gradient of the potential, which is equal to rho free. And then if epsilon is constant, if you have a uniform dielectric, let's say, then you can just take that epsilon out of these derivatives, and you end up having lambda squared is equal to lambda squared phi is rho f over epsilon minus. Just compare it with the vacuum equation. So the only difference is wherever you see an epsilon 0, put an epsilon, and you get the potential in a medium, assuming that epsilon is constant everywhere. So in this sense, replacing epsilon 0 by epsilon takes into account all these surface charges, etc. But we can do something else. We might avoid replacing epsilon by epsilon 0. In that case, we are not taking into account the effect of the bound charges. We have to add them. So the bound charges are only on the surface, so we are adding their contribution to the electric field here. Now, the bound charges also change my charge at the position of my. So you see, in this region, I have a dielectric. I put a charge plus Q. It will, well, this point is kind of the boundary of my dielectric. That point is not really in my dielectric. So there will be a surface charge on that dielectric, which will change my Q to some other charge. And that thing I can take into account by replacing it by epsilon 2. Now, this is the effect of the surface charges in the interface. This is the effect of the bound charges at the position of my charge. So they will kind of hide my charge. So I have taken all the charges explicitly in this expression. Now let's come to the method of images. What does it do? Method of images tells me that, well, let's write instead of the electric field, let's write the potential. Now, method of images tells me that this integral let's say in region 2, that integral is nothing but equal to q prime over r minus r2. So this surface charge density is such that the whole integral can be written in this form. Now, then the question is, how do we relate that integral to the region in z less than 0? You have seen complex calculus, right? Okay, I will end it today, and hopefully next week we can see how it will be related. I don't know the relation at the moment, but my suspicion is that if you remember, have you seen this expression? Basically, Dirac delta function? Okay. If you haven't seen this, probably I will not be able to explain it. Anyway. Still, that's a nice question to think about. So see you on Tuesday.